Hello, Chem 1. Last time we were together, we talked about how we organize electrons around a nucleus in orbitals using Schrodinger's equations. Today, we're actually going to work through that process together and do some examples. Let's get started. Remember, we've been kind of using the analogy of an address or a hospital complex where we talk about a building, a floor, a room in the floor, and then there's two beds in that room. There's two electrons that can go in every orbital. I'll continue to keep referring back to this analogy because I think it's helpful you to understand what we're doing with the electrons. Also, just to review, remember we talked about the Pauli exclusion principle. Every electron needs to have its own unique address. The off-ball principle, which means we start at the lowest energy level, energy level 1. And Hund's rule, which means within a sublevel, we're going to space those electrons out as much as we can. We'll be referencing these rules as we do some examples. This is also a very helpful worksheet to be walking through as we do these together. When we are placing electrons, we're always going to start here at the very bottom and work our way up. So for instance, 1s would be the first orbital we fill, then 2s, then we'd fill all of 2p, 3s, 3p, and so on. All right, let's do some examples together. There's two different representations we're going to use today. We're going to use the orbital model and electron configuration, which is more of a shorthand. So with the element hydrogen, the first thing we need to know is how many electrons are present. Hydrogen is the first element on the periodic table, which means it has one electron. And that first electron will go in the lowest energy level, which is 1s. The way we represent this is by writing 1s and then putting a line to signify the room of 1s, and then the arrow is the electron. It's saying that there is one electron in that room in the 1s sublevel. The shorthand way to write this, or the electron configuration notation, would be simply to write 1s, and then you put an exponent on the s that tells how many electrons are there. So in this case, there's one electron in 1s, and so we just write it like that. Let's keep going, and I think you'll see the pattern. Helium has two electrons because it's the second atom on the periodic table. One s is the first orbital, and remember every orbital can hold two electrons, which is how many helium has. So we draw one arrow up and one arrow down to show that each electron has different spin. The shorthand way to write this would be 1s2. Pretty simple. Lithium has three electrons. So we'd put the first two in 1s, and then you might be thinking, well, what comes next? If we look back, we see that the second energy level and the s sublevel has a room that we would fill next. So 2s would have one room, and we'd put our third electron in that room. The shorthand way to write this would be 1s2, 2s1. We've placed all three of lithium's electrons. Now let's go to boron. Boron has 5 electrons. So the first two go in 1s, the second two go in 2s, and the fifth electron goes in 2p. Notice that I've put 3 rooms in 2p, or 3 orbitals. That's because p sublevels hold 3 orbitals. If we look back at our sheet, you can see that a p sublevel has 3 orbitals. That's why we put 3 rooms or 3 dashed lines above 2p. So let's go ahead and place that last electron. The shorthand way to write this, 1s2, 2s2, 2p, 1, because it has one electron in 2p. All right, now let's look at nitrogen. Nitrogen is the 7th element on the periodic table, which means it has 7 electrons to place. The first 4 you should know by now go in 1s and 2s. But now we need to fill 2p, but we've got to pay attention because this is where Hund's rule comes into play. We cannot put these last 3 electrons like this. That breaks Hund's rule. Hund's rule says that within a sublevel we have to spread those electrons out. So this would be the correct way to do the orbital model for nitrogen. And if we write out the shorthand, 1s2, 2s2, 2p3, you'll notice that the orbital model shows you more information. It shows you where those electrons are, what orbital they're in, where the shorthand, you just know there's 3 electrons in the 2p sublevel. You can't see that they're spread out using Hund's rule. Let's skip over oxygen for the time being and look at vanadium. Vanadium has 23 electrons. Okay, there's kind of a lot going on here. First, we went 1s, 2s, 2p, 3s, 3p, 4s, and 3d. Why did we do that? Well, if we look back at our chart, we can see that after we fill 3s and 3p, we actually fill 4s first, and then we fill 3d. So you need to base your orbital models based on the chart and the order that we go on the chart. There's a reason for all this. We're getting to that. We're just not there yet. The other thing you'll notice is that in the last sublevel, 3D, I spread out those arrows to make sure they're not bunched together. We're following Hund's rule. And if you count up all my arrows, you'll count to 23, which is the element of vanadium. All right, good job. I hope that gave you a pretty good idea of what an electron configuration notation should look like. Hopefully now you can do some practice by yourself and get used to the pattern of electron configuration notations. It will become easier the more practice that you do. Good job today. Keep up the good work. We'll see you soon.